You're gonna put 3 in a row this week.
Yeah, get back to 500.
Yeah. Okay, so now we get to continuity. What word is very closely related to continuity that you know of? Continuous. A function is continuous if it has an x value everywhere from negative infinity to infinity. Thus, it is a continuous function. This first function here, the w, is continuous. Every single, I could put any number into that function as an x, and you'll get a y value out of it. So we're good. Now, if it's not continuous, sometimes we have, this comes from a piecewise function, it's called, where you have a function, and then there's a place where a number will not work in that function, but you have a number replacement that's not that number. So this is from a piecewise function. This is called a removable discontinuity, where as you're coming in to that point, and you're going out of that same point. Okay? So it doesn't like jump around. The graph is going towards a point and then continues from that point, but that point isn't a point. Okay? That's called a removable discontinuity. Okay? A removable discontinuity. Calvin, you paying attention to any of this? Okay, sounds good. All right. Here's another removable discontinuity where they just don't have a number up here. It's just a dead spot. A hole in the graph is what we call it. Now, this is a non-removable discontinuity. A non-removable discontinuity jumps around. Okay? So it's a function and then another function where there's a jump in between. It's called the jump discontinuity, but this is non-removable. This one and this one are both non-removable discontinuities. And this one we see a lot. This one we see a lot. That function is probably something like 1 over x minus 1 or something like that. Okay? Because you get this happening, and it's actually a hyperbola when you have a variable in the denominator. Okay? So it looks like we have an asymptote here and an asymptote here. And we'll talk more about asymptotes next time on Wednesday. Okay. Identifying points of discontinuity. Now, it would be great if your graphing calculator did this, but which of these two functions look like they have a discontinuity on them? The right one, because there's a hole in the graph. There's a little hole here. Now, your graphing calculators aren't going to do that for you. Sorry about your luck, but they're not. So let me put in a function, y equals, come on. All right, clear. Let's go parentheses x squared minus x minus 6 divided by x minus 3. And let's look at that graph. It looks like it's a continuous function here, right? You don't see any holes, do you? Anybody see any holes? No. If I trace to 0, I get 2. If I trace to 1, I get 3. If I trace to 2, I get 4. If I trace to 3, I get, uh-oh. What's that? Nothing. Because when you divide by x minus 3, you learned this morning that you cannot have what? 0 in the denominator. So if we put a 3 in here, it gives you a 0 in the denominator. Can't do that. Okay? So there's a hole in the graph. Does it show a hole in the graphing calculator? No, it doesn't. Okay? It doesn't. And then if you set it up perfectly, it'll show a hole in it. So if we go zoom, and we go to the integer window, which is down a little bit. 8. Zoom 8, and we go to 0. Okay, let's go zoom 6. Get it squared up. And then zoom 8, enter. Here's the integer window. And if I zoom in on this, I don't know if I can zoom in on this. But in the integer window, do you guys see there's a blank spot right there? There's a blank spot right there. So it does show up as a whole on the integer window. But to be on the integer window, you have to go zoom 6 and let it graph so you're at 0, 0 as your center point. Then zoom, and then 8, and then enter. And puts you in what's called the integer window. So every dot on here is like a whole number, or an integer, a negative, positive, or negative whole number. Okay? So there are holes in the graph, okay, but they're just hard to see most of the time on a graphing calculator. Okay, increasing, decreasing functions. This is an increasing function. It looks fairly flat, but it's always, always, always increasing. It's always going to increase just a little bit. Even though there's asymptotes there, it's always going to increase just a little bit. Here's a fully decreasing. No matter where you go, it's always going down. Here's a constant function. And this last one is it's decreasing from negative infinity to negative 2. And negative 2 is included. That's important. Okay? It decreases until negative 2, and then you put in the bracket saying it is included. Okay? And then we go, it's constant from negative 2 to 2. Both in brackets because they are included. And then increasing after that. So decreasing, negative slope, constant, 0 slope, increasing, positive slope. Okay? And yeah, we don't have to talk about that anymore. This one. Imagine graphing that thing. Okay? What they say is this is what's called a piecewise function. Yeah, you have certain stipulations on it. And so with their certain stipulations, they came up with this graph. Where is it constant? Well, it's constant from negative infinity till right there at negative 3. And where is it constant again? From 2 up to infinity. Otherwise, it's increasing from negative 3 to 2. So it's constant from negative infinity to negative 3, and from 2 to infinity, and then it's increasing from negative 3 to 2. Okay? Now, this one, I won't ever give you a problem like that in here. Okay? You'll see these in AP Calc. You won't see these in here. Okay? All right, boundedness. Okay? I'm going to go back to here and talk about boundedness. Okay? This graph right here, it looks like there's an asymptote maybe at about 2 and about negative 2. There'd be asymptotes. So this one would have an upper bound of 2 and a lower bound of negative 2. Okay? It won't go any lower than negative 2, so that's its lower bound. It won't go any higher than 2, so that's its upper bound. Makes sense, right? What would this one have a bound of? Would it have an upper bound? No, it goes up forever. Would it have a lower bound? Yes. This one would have a lower bound of 2. Okay? This one, we wouldn't talk about bounding on that one. But this one would have a lower bound of 1. Okay? It's just the range. So that's boundedness. And then absolute and local extrema. Okay, here's a function that goes like this. Okay? What's the absolute maximum of that function? Infinity. It'll keep going up forever here. We assume that it keeps going up forever, so its absolute maximum is infinity. The absolute minimum here is negative infinity. It'll go down forever. This point and this point are called, this is a local max up here, and this is a local min right here, okay? They are local. They are within the endpoints. So there's the lowest point over this range, this domain, and there's an upper point, a max point over that domain, okay? Those are called relative extrema, okay? When you have a local min or a local max, okay? A parabola has no max, but it has an absolute minimum, okay? Whatever the y value of this vertex is its absolute minimum, okay? So you'll be working with that. So if you have something like this given to you and you have to figure out your local mins or maxes, you put it into your graphing calculator. On y equals, clear it out. So x raised to the fourth minus 7x squared. Whoa. Let's try that again, Mr. Rierschbach. Fourth, arrow over, minus 7x raised to the fourth, 7x squared, plus 6x. Okay, if I just graph it, who knows what it's going to look like? Ooh, that's really ugly. So I'm going to go zoom 6 and graph it on my 10 by 10 window. And I know it's going to go something like this. In general, it goes something like this. I've got to find each of these points. How do I find the points? Well, I use second trace to find them, okay? And then I want, the first one is going to be a max or a min? Min. So I want to find a minimum, so I go 3, and I'm going to go to the left of that minimum point. So I'm going to see my little cursor thing. Since it's flashing right there, I know I'm to the left of this point. And I'm going to press enter. And then I'm going to go to the right of that point till I see my cursor again. So I'm on each side of it. I'm going to go enter again. It says guess. I don't want to guess. I just want to find it. So you're going to have a local minimum at negative 2.06, comma, negative 24.06. Okay? That's where your local min is. Then you're going to have a local max right here. So you go second trace. I'm going to want a maximum this time. So I go 4. Got to find my cursor. There's my cursor. Go to the left of that point. Hit enter. Go to the right of that point. Hit enter. And then hit enter again because I don't want to guess. And it's 0.46 and then 1.32. 0.46, comma 1.32. And then the last minimum, second trace 3. I'm to the left, hit enter. I'm to the right, hit enter, and hit enter again. The last one is at 1.6 and negative 1.77. So the maximum occurs at the x value. The maximum value or minimum value is the y value. Okay, where it occurs is the x value. Its value is the y value.